So I wanted to introduce your guest speaker. First of all, I'm Gail Slumman. I'm with Northrop Grumman as the chief engineer at our local facility here, right at the Spectrum Center in Kearney Mesa. It's just a few miles away. And what we do there are primarily airborne and networking systems. We're part of the Airborne Maritime Systems group in San Diego, and we pride ourselves in making the tactical data network work. But we have here a very honored guest, our VP of Engineering for our Information Systems sector, and I'll give you a bio brief here. So Neil Siegel is the Vice President and Chief Engineer of Northrop Grumman's Information Systems sector. He leads the sector's technology and engineering group. He is responsible for a large number of successfully fielded military intelligence systems, including the successful Blue Force tracking system, the Forward Area Air Defense System, the Army's first unmanned aerial vehicle, and many others. He has also led work for the steel industry, the movie industry, and other commercial enterprises. Very broad background here. He has a doctorate in systems engineering from the University of Southern California, where his advisor was the noted computer scientist Barry Baum. How many of you are computer science majors here? Okay, you've heard about Barry Baum and his techniques for estimating software productivity? Maybe? Yeah? Okay. Among many other honors, he also was elected to the U.S. National Academy of Engineering in 2005. He is also a fellow of the IEEE and was awarded the IEEE Simon Ramo Medal for Systems Engineering and Systems Science. So welcome, Dr. Siegel.
Thank you very much. It's great to see such a wonderful turnout. I don't know if it's me or if it's the free pizza or what, but I'm really glad you're here. So I'm going to talk about something a little different than maybe a lot of the lectures that you get. It's not primarily a technical lecture, although I'm happy to discuss a lot of the technology that we have applied, and I have some examples. So I only have 5 or 6 slides, so we can make this very interactive. I'm very informal. We're a small group, so just raise your hand if there's anything occurs to you that you'd like to ask. When I left school, I felt that I was very poorly prepared for what I encountered when I left work. I actually worked my way through school as a musician, and so my first 8-hour day behind a desk was after I finished and after I graduated. And I really had no idea of what to expect. And academically I felt very well prepared, but kind of socially and so forth, I felt very poorly prepared. So I think I always found it worthwhile to go out and talk about what is it that we do in private industry. Come on in, we'll find room for you. So Northrop Grumman is primarily an aerospace company. We do a lot of work for the United States government, so we do a lot of defense contracting. We do a lot of other things too, and I'll describe some of those. The work that we did for the steel industry and that we did for Warner Brothers and Sony Pictures and stuff like that is also part of our portfolio. We do a lot of work in the public health sector and so on and so forth. So we do a lot of unusual things. I've also worked overseas. I lived in the United Kingdom running a project for the British government, and I've ran many projects in the Middle East. So I've got a little bit of exposure to how we do it in other companies and in other parts of the world. And actually, there's really quite a bit of similarity to how private industry works. So I'd like to talk about that and engage in a discussion like that. So can I have the first slide, please? So, I work for a company called Northrop Grumman, and as I said, we're primarily an aerospace and defense contractor. So, this is my company. We're a big company. That's the first thing. There are 100,000 people. When you work in a big company, there are some disadvantages. It has a lot of rules because you can't have 100,000 people just doing anything they want. On the other hand, you have 100,000 very smart colleagues. And if you can learn to navigate the rules, you can do pretty much anything you want, and you can get the intellectual stimulation and the benefit of having all those smart colleagues. If I need expertise in some field, the chances are I can find it very quickly inside my own company which means, I can get access to information very quickly and with real levels of expertise. And that's a real asset that comes with a big company. Now, I actually worked for a small company for a while after I'd worked. I came out of graduate school, I joined a company that later got acquired by Northrop Grumman, and 3 years later, my boss and my boss's boss came to me and said, we're going to leave the company, we're going to start a startup, do you want to come with us? And so I was one of 5 people that went and did this startup company. So I worked at small companies too. And I stuck with that for 7 years. We went public, we grew to about 1,600 people. But I decided I wanted to work on big projects. My life ambition at the time was to be the chief engineer on a billion-dollar complex engineering project. And you can't do that at a smaller medium-sized company. They don't do jobs like that. And so I went back to, we were called TRW then. It's not part of and have been there ever since, and have had a whole series of jobs. And I'm actually going to talk a little bit about my career path in one of the slides, because I think you'll find it kind of interesting. It's the opportunity in a big company to do an incredible range of things and have a wonderful set of life experiences. Come on in. We'll find room for you somehow.
There's room over here. Please come on in.
There's a chair here that somebody can have. I need it. I'm standing here, please. The lady there, please. Ladies first. Ladies first. Okay. So we're a big company. We're all over the place. We are based in the United States. Okay. So we're based in the United States, and most of our employees are in the United States. But as you can see, we actually do work in a lot of countries. We have major offices in Europe, and we have employees doing work for customers in more than 20 countries, and all 50 states. So one of the nice things is if you come to work for us or a company like us, you can pretty much choose wherever in the world you want to live or wherever in the United States you want to live. In a world of email and telepresence and video conferencing and stuff like that, we tend to let people live where they want. Which is also kind of, so we build neat stuff. So I got some of the obligatory kind of neat pictures here. So we have a part of the company that builds airplanes. So the top center, that's called a Global Hawk. That is a 737-sized unmanned aircraft. It can fly at 65,000 feet for 3 days without refueling, carry several thousand pounds of payload, cameras, and all kinds of other stuff. It's used obviously by the United States military. It's also used by organizations like NASA to do upper atmospheric research. You can kind of think of it as a satellite that you can launch and recover. So if you have, 65,000 feet, you're getting to the point where you can, it's almost low space. So I think the formal boundary of space is 100,000 feet. And so you can do all kinds of research with a platform like that. In the upper right-hand corner is an unmanned air vehicle that is a combat aircraft that's designed to take off and land from an aircraft carrier. So we've actually done first flight on that machine, and it will do its first carrier landing in about a year. It will be the first unmanned plane ever designed to be take off and land from an aircraft carrier. I don't know if you've ever thought about an aircraft carrier. I actually spent a weekend on an aircraft carrier once. And in heavy seas, that back deck of the aircraft carrier moves up and down about 20 feet. So try and design a machine that can land on that. That's a pretty interesting trick. This on the left is something that we built for the U.S. Army and the Marine Corps. About 15 years ago, we started a project to say this is the information age. Let's bring information down to every soldier, every Marine, every helicopter, every tank. And you can kind of think of, you'll get it. Think of a video game that has a screen there with a map with red and blue icons showing you where everybody is. It doesn't, people who like us who've grown up with the information age, that may not seem like much, but for all of history, combat had been conducted basically with what you could see, what you could hear over a radio. If you were in a tank, it's an armored vehicle, so you're all closed up, and they have a little prism system that you can look out that they call a vision block. And so you can see, about this much of the world, and it's full of dust and smoke, and that anybody could do anything was a kind of a bloody miracle. So we built that system for the U.S. and every tank, helicopter, jeep, and most individual dismounted soldiers in the United States military today have one of those systems. That was actually one of my own personal accomplishments. I was the program manager for that system. You may have heard of the Hubble Space Telescope. This is the replacement for the Hubble Space Telescope. So it's actually IR rather than optical. That mirror is 25 feet across. It will be the largest optical aperture ever put into space. It operates at 3 degrees Kelvin. All the optics and electronics operate at 3 degrees Kelvin. So this structure is a sun shield. It's about 100 feet long, 50 feet wide. It's a gigantic thing. Since we can't launch anything that's bigger than 5 meters, that's the largest launch fairing. That whole thing folds up into, a 5-meter tube, and then in space, at the temperature of space, unfolds, cools itself. And then, by the way, unlike the Hubble, which flies in a low Earth orbit of only 200 miles, this goes at what's called the Lagrange points. So it's 250,000 miles from Earth. So no possibility of servicing it. So it has to be right the first time. So it's about a $10 billion instrument that we're building and should be ready for launch in about 4 years. We build the nation's ICBM fleet, the Minuteman missiles. We are the largest contractor on the next generation fighter aircraft, the Joint Strike Fighter. We build unmanned helicopters. All 4 of the spacecraft that have left the solar system were built by our company. So the only 4 objects in all of human history that have left the solar system were built by us, here in California, by the way, in Los Angeles. Pretty interesting company, a lot of interesting skills. What doesn't show up on a chart like this is that computer science, information technology, system engineering is behind everything. My parents were both aerospace engineers, and when they built spacecraft in the 50s and 60s, they basically had no software in them. I mean, there was a time when telephones had no software in them, right? But today, everything has software in it. So computer scientists, system engineers are all over all of this stuff. More than half the cost of an airplane program these days is the avionics software. Sir, you had a question?
You said you do work in other countries for, basically for organizations that are not the U.S. military arm, but most of this looks like it's proprietary U.S. military technology that can be used back.
Right. So, great question. So, in the United States and in most other countries, the United States maybe is a little more pedantic about it than others, there are export restrictions. So when you invent something, whether you're a military contractor or not, this applies to Oracle as much as it does to Northrop Grumman, you have to get permission from the government before you export a technology. And so we have to do that, just like every other company in the United States has to do that. But if you're exporting to allies, you can get permission to do that. So I went and ran a contract bringing United States military technology to the British government. So I ran a contract for the Ministry of Defense. I had about 40 American citizens over there with me, and I had about 800 UK nationals working on the project with me. So, but you have to just get permission to do it. And there's forms and rules, but in a 100,000 person company, you have people who can specialize in knowing how to do that. So that's what we do. It's pretty neat stuff. Not really kind of shown on this chart is, because it doesn't make pretty pictures, is the work that we do for some other sorts of customers. So there's an organization in the United States called the Centers for Disease Control, and they are the public health specialists in the United States. And they actually, in a world like today where there's so much airplane travel, you can't really have public health in one country. because people get on an airplane and go somewhere else, and diseases and things move around the world. So they're really kind of the public health specialists for the whole world. And I have 1,000 people in Atlanta, Georgia, working for the Center for Disease Control, doing all of their mission processing. So we model, how does malaria spread? How does the interaction between mosquitoes and people and other animals and climate and roads and all that, so how does that work? And therefore, because you have to make decisions when something starts to happen, you only have a certain amount of vaccine, or you only have a certain number of health professionals, and it's an operations research problem, it's an optimization problem. When do I intervene? How do I intervene? And we do all that processing for the United States.
So for the benefit of our students who are considering careers, so a lot of our students will go to internet companies like Google, where things get turned around like on a 6-month basis, or maybe they'll go to Microsoft, a 2-year product cycle or something. A lot of these efforts are a decadal effort to field one of these really big systems. And so I'm curious, how does that, what kind of, when someone comes in at Northrop Grumman and works on one of these, how does that get broken up? Should they expect that they're going to be on the Joint Strike Fighter for 10 years until it's out? They work on pieces and move around?
Yeah, that's a great question. So you have a lot of choice about this kind of thing. We like to have assignments of a certain minimum duration, because we want you really to kind of dig in and learn something and get over the learning curve, and then be in a position to really make a contribution before you move on to a next assignment. If you asked my opinion, the optimal assignment is about 2 years. 2 years, 3 years. If you start staying longer than that, you're probably ready. You're probably made all the contribution you're going to make to that problem, and you would benefit from working on a new assignment, and the program would benefit by getting a new point of view. So you're absolutely right. This job is a 15-year job to build the spacecraft, start to finish. We won the contract in 2002, and it'll probably be launched in 2017. And of course, it'll be operated for 10 or 15 years thereafter, and that takes a lot of smart people too. So in a lot of these jobs are really kind of 30-year jobs, and nobody stays on a job like this for 30 years, right? So you go and you work on some portion of it for 2 or 3 years, and then you're ready for a next assignment. Now, if you really have gotten into it, you can stay. And then what you can do is, because you become an expert in that field, you can move up, right? So we have been the prime contractor for the United States Land Force, land-based intercontinental ballistic missiles, since the program started in 1954. We are the only people in the United States that have built that job. And there's nobody on the team who's been there since 1954, but there are people on that job who have spent their entire career on that job because they wanted to, but they didn't have to. We don't find that, spending 4 months or 6 months on assignment and then moving on is the best thing. You haven't really learned everything you can learn from that assignment, and so on and so forth. I will tell you something about a business like ours. We're not a business where the meat of the business is factories. We're not a business where the meat of the business is patents or industrial processes. The meat of our business is our people. And so we work very hard to recruit great people. We like for our people to get emotionally involved in the missions of our customers, because that makes it very exciting. It's a calling. It's not just a job. And then we do a lot to make it a good environment for our people. Training, job rotations, career counseling, rapid promotion. In some sense, if you got an organization where people are your only asset, then when you get a hold of some people who you think are really above average in potential, you're going to do a lot of special things to nurture them. So when I'm done, Gail can talk to you about some of the programs that we have. So, for example, I have a program that I run called Future Technology Leaders, where we go out. I mean, we hire about 3,000 people a year in my portion. I have 15,000 engineers, 25,000 people in our sector of the company, and we hire about 2,000 to 3,000 people a year because people retire, a few people move to other parts of the company, a few people actually leave the company, and so on and so forth. So we hire, call it 2,000 people a year. When you're hiring that many people, you're hiring average people, right? With a lot of large numbers, right? You all understand what it is. And so and that's done by our projects and by our human relations organization. I have a completely disjoint hiring chain that I call Future Technical Leaders, where I build partnerships with the best universities. I build relationships with faculty members and try and discover who the best master's and PhD students in the right fields are. And then we have a special hiring program for these people. And then we do special mentoring of those people and try to do fast promotions for those people and so forth. So we actually do a lot to nurture and make our people like the work experience at our company, because people are our only asset. Yeah, we have manufacturing plants, but it's a teeny portion of our overall business. We are mostly a research company who build, we have to build that, but we're only going to build one of them. It's not like car companies that can do a little bit of research, design a car, and then build 5 million of them. Right? That's not what we do. For us, if we build 100 of something, that's large volume production. We're actually building 200,000 of those, and we ended up hiring somebody else to build the box. And in fact, we don't even have anything to do with building the box anymore. The Army buys that directly from the manufacturer, because building 200,000 of something is not our culture. Right? We like to build we build one of a kind or first of their kind things. That's what we like to do. When we do something, it's usually because somebody else has said, that's impossible. Can't possibly do that. That's when we like to do it. Because that means we're not competing on price. Right? When I won this job, this is an interesting thing, because everybody thinks, you got to compete in the marketplace and price is everything. When I won that job, I bid twice as much as the next bidder. There were 4 bidders. I bid twice as much as any of the other bidders, and we still won the job, because the Army had experimented with it with another company, had experimented with their own research labs, had decided that parts of the problem were impossible. How do you form the communications network? We can talk about that technology a little bit later. And I came in and showed them how we could do it, and they basically said, we have to have your team at any price. So that's what we like to do, is be so obviously the best. And that way I can afford to pay people well, I can afford to give them vacations and pensions and all that good stuff. Got the next slide? Here it is. So I described the setting. What does an engineer do? And this is where we get into stuff that I felt 30 years ago, when I first joined private industry, I was not well prepared for it. I was technically very well trained, but I didn't understand what an engineer or a computer scientist did when they showed up on the job. And we'll talk about this more, but the first thing that was really different is that it's a team activity, right? So here you are in the academic activity, and you have to do your own homework, right? You're not allowed, within some measure, you're not even allowed to collaborate. If you're going to do a thesis or a dissertation, that's your own research, that's your own writing. If you do academic papers, there's some collaboration, but it's with a small number of people usually. And you show up at a place like us, and the typical project is 100 people. And so there's this big social dynamic that you have to learn. Actually, it turns out to be wonderful, because these are colleagues, this is intellectual stimulation, but it's so different than what we're conditioned as we go through university to optimize on, right? So we get there. So first thing is you discover that it's actually, first and foremost, you have to understand the customer, okay?
And so this is kind of counterculture. I'm the chief technology officer, chief engineer for this gigantic organization, and I'm going to tell you that the basis of competition that we bring to the market is not first and foremost technology. And so let me explain that. Every organization, that's a customer or potential customer of ours, has a business process by which they do work, right? It might be a U.S. Army division, which has military tactics. It might be the Customs and Border Patrol, that has a business process by which it takes fingerprints and checks in a computer whether you have a green card or not. It might be the Centers for Disease Control that's trying to monitor public health all over the United States and in many parts of the world, and trying to understand if there's actions that need to be taken. But all these customers have business processes. And the way a company like us operates is that we look at their business processes and we look for opportunities to create revolutionary improvements in their business processes. Okay? So if you think back to that computer in the tank that I showed you, okay, the business process for how armored warfare was conducted around the world is that people had single-channel push-to-talk radios, basically fancy walkie-talkies, and they had that little prism that allowed them to look out, to see this little teeny piece of the world right outside their tank. And that's how they conducted armored warfare. And we said, we're going to give you a completely different business process. We're going to basically give you an electronic map, and you're going to see right there, right, like it was a computer game, where everybody who's part of your combat team is, and everything we know about the enemy, and we're going to show you where the minefields are and where the bridges are that are contaminated with chemical spills and all that stuff. And you'll have 1,000 times as much information as you did when all you had was what you could hear over the radio and what you could see at the vision blocks. Okay? And then what we did, having created this really compelling and interesting business process, we had to convince them that it was feasible. And that's where technology comes in. So technology is a dependent variable and not the independent variable of what we do. So the best employees are the ones who take the time to learn something about a customer. Okay, so I took the time to learn something about the U.S. Army. I was never in the military. I knew nothing about, what soldiers did or anything like that. But I took the time to learn, and that allowed me and my team to create this revolutionary ConOps, and then we could go to our technical skills and create the technology to make that new ConOps feasible. But the independent axis of our creation was the new business process. Revolutionizing the business process, and then you use the technology to make it feasible, affordable, whatever, okay? And so the first thing that you have to do is to understand what's the customer. And this is one of the nice things about having all these colleagues, because they can teach you, and they can, some customers have written artifacts, and some customers you just have to go and talk to people, or you have to go and watch, you have to go and participate. We actually have opportunities where some of our customers will let our employees go and work with them for 6 months. And so that increases your value, because now in one brain I have computer science and engineering skills and domain knowledge of the customer. And that combination, in our view, is magic, right? And so when you do that, then you can really understand the customer and how do they determine value. So you talk to a radio engineer, and they'll say, I've got this great idea, and I can redesign the antennas, and I'll get 3 dB more link margin. Well, does that help the customer or not? It might, or it might not. You need somebody who understands both what you just said, because they understand engineering, but also understands the customer and can make that connection and can socialize those ideas with the customer, right? And we're engineers and scientists, so we measure things, right? So you need to create metrics that will resonate with the customer, that describe the technical value proposition that you're proposing. So, okay, what does it do for the Army to have this computer in the cockpit of the Hank or the helicopter? What does it do for the Centers for Disease Control to have all this modeling capability? Does it actually help them eradicate epidemics earlier or not? We might think it's intuitively obvious that it would, but I could cite chapter and verse for you of instances where things that seemed intuitively obvious actually weren't true. Okay, I was building a system once where I had my radio vendor company say, great news, I figured out a way to double the data rate of your radios. And I said, that's great, hold everything. And I went over to my modeling people and said, now, drop that doubled data rate into our model of this whole complex system and tell me in terms of the metrics that matter to the customer, do they get better or not? They didn't, because it turned out there was another bottleneck. And so I went back to the radio vendor and said, actually, instead of doubling the data rate, I want you to do this other thing. It had to do with, from the time they pressed push to talk, how long did it take for the radio channel to get set up? And it turned out that reducing that setup time was much more valuable for the way that the customer measured value than doubling the data rate. Okay? And so understanding the customer's value proposition allowed us to make the right technical decisions and apply our computer science and our system engineering in a way that actually added value to the customer. So we do that. How do we do that? Well, you have to create what we call a trade space, right? So you've probably all heard that term. So you want to create a range of options. Now, people hate ambiguity, right? So people tend to converge down to a preferred option very quickly. And what I'm always telling my team is don't do that. Keep the trade space open and really do modeling or benchmarking or facts-based analysis before you converge to an answer. We like to converge quickly because we hate ambiguity, but if you converge the trade space too quickly, you likely missed the real best answers. So it's our job to make sure that the trade space is robust and that we traverse it in a way that's fact-based, that we measure the effectiveness of our candidate solutions in the terms of the metrics that resonate with the customer, right? So it's that measure and not the doubling of the data rate, and so on and so forth. And then another thing that's very important is if you're building big things, whether with us or with Google, I mean, most useful things happen in large teams. Most useful things in our world, in the technical world, you know, the newspapers like to write stories about one person over the weekend, you know, wrote some new killer app, and that happens sometimes. But Google, for example, is an enormously complicated enterprise, right? You know, tens of thousands of servers, millions of lines of very complicated code that do all that MapReduce processing, for example. That's the engine that drives their search capability. That was not two people in a weekend, you know, doing that work. And same thing in our industry. Most of the worthwhile things are projects are 30 people or 50 people or even hundreds of people. So doing things at scale is very important, and the engineering rigor that we learn in school is how you do things at scale. And then maybe the most interesting thing that I didn't mention, so I think I mentioned that I'm a musician and I put myself through college as a musician. So I kind of entered the world, you know, looking at the artistic side of things. And what I discovered is that what we do is kind of half art and half technology. And if you want to be a good computer scientist or a good system engineer, you have to bring both perspectives. And I'll talk about that a little bit more. Okay, next slide. Sir.
Well, one quick question. So how often, it sounds like most of the time, you're being driven by a customer who wants to purchase a particular capability or has a particular problem and would like that problem solved. How much activity goes on that is proactive, where you anticipate, okay, we think customers are they don't realize they're going to have this problem.
Right.
But we should start working on it because we know they're going to ask for it in 2 years, even though they don't realize it.
Right, that's a wonderful question. So the answer is about half and half. That is what I always tell our people is that, half of what we propose to do should come from listening to the customer, and the other half should come from our having gone out and tried to understand what they're really trying to do and getting ahead of them. What I like to say is that a lot of our customers, for them, the future is 3 minutes from now, because they're so busy conducting their mission, that they don't really have time to think of what could be better. And if you ask them what they need, they'll very often talk about, I need to automate my existing business processes. And they won't be thinking about what could revolutionize my business process. And so we can use our understanding of what they're actually trying to do both, a little bit of both. So sure, we do a certain amount of work that is just what they asked, which is generally automating their existing business processes. But we also strive to create those revolutionary business processes even in advance of them asking for them. And that's actually the most fun part. Sir?
So, I'm going to present what you do, probably more than me, but there's at least two different pieces to every project that one can partition it into, at least by one dimension. And one is the researchy side, where you're probably building some proof of concepts that, this is in fact feasible or technically possible, and there's proof of concept that works.
Mm-hmm.
And then there's actually the product version of that, which is usually almost nothing like the original proof of concept that requires monumental effort to get to. One is definitely more researchy than the other. How do you do those two pieces of every project? Is there a dedicated team that does research side? Is there a dedicated team that does implementation and productization?
Right.
Or do they mix, or how's it work?
Yeah. So another very good question. So the answer is, of course, we do both. The research side is usually characterized by being smaller, right? You're trying to identify the new revolutionary concept. You're trying to figure out what technologies can we beg, borrow, or steal that would help us populate that new business process, and which pieces do we have to invent because nobody does them yet. And then you have to go and invent those, right? And then you have to kind of put it all together in a prototype. And generally, we do that with our own money, okay? Because that allows us to be well ahead, as the professor just mentioned, to be ahead of the perceived need that creates differentiation in the marketplace. And then usually what we do is some portion of the people who participated in the research will transition to at least the early portion of the implementation phase, where you have to build a version that meets a cost objective, that meets a reliability objective, that can be used by normal people and not just by PhDs in computer science, so on and so forth. It can be manufactured. Lots of prototypes don't think about what it takes to be manufactured and stuff like that. Can be dropped, all those kinds of things. But usually what we do is we like for some portion of the research team to transition to the beginning part of the implementation team to transfer knowledge, but it also broadens their perspective. It gives them the chance to learn a little bit about what is it like to design a product that can actually be used by an ordinary person rather than a PhD in computer science? What is it like to design a product that can be manufactured rather than, hogged out of blocks of aluminum by a machine, or one-of-a-kind machinist or something like that? And that elevates their perspective on the world. And then they go back and do the next research project. They've got more perspective. And so I tend to like my best researchers to kind of alternate assignments. They'll do research, they'll invent something, they'll follow it into the engineering and productization side at least part of the way, and then they'll go back into the research side and try to invent something new. And we find that they find that very satisfying, that combination of things. Sir?
Sort of a follow-up to that question, how far out do you look ahead in terms of research prospects? Do you think like 3 to 5 years ahead, or 5 to 10, 20?
So another interesting question. So the way I mechanize it in our part of the organization, now every business has its own cycle time, right? So the spacecraft business operates on definitely a slower cycle time than the information systems business that I'm the chief engineer of, right? So they kind of operate on a 10-year horizon, right? One generation is 10 years for them, right? In our business, we think of one generation as being about 3 years, okay? So I've divided our research program into 3 parts. And you can kind of think of it as the stuff we're doing now for the proposals that we're going to bid later this year or next year, right? And that's not really research. That's almost kind of taking research ideas that have proven out and packaging up as prototype concepts for customers. And then the stuff that's kind of aimed out 2 or 3 years, which is, the next revolution, the N+1 version of a customer need, trying to do that revolutionary business process and implementing it. And then the third pot is the stuff that's aimed at longer than 3 years and we're experimenting with completely new ideas that someday might become implementing technologies for some new business process, but we don't even know what yet. So to give you an example, we started experimenting many years ago with the problem of how to control computers via gesture without having to wear gloves or something like that. How could you do that? And we didn't really know what products we would put such a technology into or anything like that. We just had a sense that the interaction between people and computers was still kind of in a primitive state, right? And that we wanted to we had a lot of situations where users found keyboards too cumbersome, found keyboards and mice and stuff like that too much training, and they wanted something more intuitive. And we thought gesture would be an interesting idea. So we wanted to see if we could do it with no gloves, no sensors, but just literally detect free air 3D hand motions. And we didn't, so that's an example. Actually, we invented something pretty interesting to do that, and we're just now, maybe 4 years later, starting to incorporate it into products that will, in the next year or two, start selling to customers. So that one really kind of had about a 5-year horizon. So for us, we work on these 3 time horizons. You can think of it as short, medium, and long. And for us, it's like 1 year, 3 year, 5 year. But for a different kind of business, it might be 5 year, 10 year, and 15 year, right? But our business, one generation is kind of 3 years. I don't think in an IT-related business it's very sensible to try and predict what things are going to be like 15 years from now. That's 5 generations. That's too much noise and too little signal, right? But if I go to my spacecraft people and I say, what's it going to be like 15 years from now? Well, they're already designing stuff that won't be launched for 15 years. So for them, it's 1 generation. So they have pretty good clarity. So I tend to think in terms of generations of technology. I like to look 2 and 3 generations ahead. In our business, since a generation is 3 years, that means the time frame I talked about. It wouldn't be sensible for the spacecraft business to only be fixated on what's going to happen next year when it takes 10 years to do something. Let me talk a little bit about public health as an example. So one of the interesting things about public health is a computer science problem is it operates at immense scale. Okay? So there are literally thousands upon thousands of data sources that you can envision wanting to use. So for example, one of the problems in public health is time to diagnosis. Okay? So think of the progression of a disease or an incident. So I'll actually tell you about an incident that I was involved in fact-finding about 10 years ago. There was a big outbreak of a public health problem that actually caused a lot of deaths in Minneapolis about 12 years ago. And at first, people thought it actually might have been an act of biological terrorism. It turned out to be a maintenance problem in a water treatment plant. And so what happened is that something bad grew on the set of filters that they were using at the water treatment plant, and a lot of people got sick, and a couple hundred people died. So it wasn't an intentional event, but it wasn't really, so we kind of did an after-action review of what happened and who noticed and what kind of signals can we set up in the system so the next time we'll find it earlier. Because when you're talking about the spread of a disease, time is everything, right? Because, one person is sick and 4 hours later, 4 people are sick, and 4 hours after that, 16 people are infected, and you get these kind of geometric and exponential progressions, and if you can diagnose the thing 4 days earlier, that's everything, right? And so what we found is that the public health people were the last people to learn about this. So we could actually investigate the record, find out the point in time when the public health people knew about this, and they could start searching for causes, and as I said, eventually, a few days later, they found this water treatment plant by looking at localization patterns and stuff like that. Well, it turned out that doctors and hospitals knew about this, I think it was like about 10 days earlier, which would have saved a lot of lives. But the public health people didn't know. So, people were getting sick, people were seeing their doctor, people were being admitted to hospitals, but nobody had the data or the mechanisms put it together as a trend, saying people from this segment of the city are getting these symptoms, and that whole segment of the city is all served from this water treatment plant. That didn't happen until about 10 days after there was this big spike in hospital admissions. Okay, so that was a signal that was missed. Okay, then we went back in time and we said, well, what do people do? Most people will try to self-medicate before they go see a doctor or go to the hospital, right? So they head off to the pharmacy, and if their symptom is diarrhea, they'll buy kaopectate or something like that, right, to try and treat the diarrhea. So we actually got some collaboration from some of the big over-the-counter pharmacy chains in Minneapolis, mined their database and saw huge spikes in certain over-the-counter drugs for treating diarrhea and fever about 7 days before the big spike in hospital admissions happened. So if you were monitoring that signal 17 days before the public health people saw it, you would have seen it, and you could have saved a lot of lives and a lot of hospital admissions. Okay? So that's the sort of thing that we look at. But if you're going to start looking at all those sources of data, the sources of data get to be very large, and the ingest rate gets to be very large, because you can just start, pharmacy chains and you just start listing all the things that you want to look at, and it gets to be very large. So this is a very large-scale computer science problem. Right? We build systems that process 1 million ingests per second, 24/7. And we build, not for this customer, but for other customers, we build private databases the size of the entire internet. And then we have, things that go searching through that data looking for trends. So these are very large-scale computer science problems. But then the next thing is the privacy, right? So we had to go through all kinds of hoops to get these pharmacy chains to release us data about over-the-counter sales. And of course, I didn't need to know names. I did need to know addresses, right? Because I was trying to localize, okay? So every jurisdiction in the world has its own set of privacy rules, right? And the European Union has a set that's very different than the United States. Lots of other countries have different ones. Within the United States, states have different rules. Even some local jurisdictions have different rules. And there are a lot of complications. So if you're going to build a cloud and store all the data in one place, whose rules apply? Is it the jurisdiction where you collected the data? Or because the cloud is sitting here, what if the cloud is sitting in the European Union? Do the European Union rules apply if all the data was collected in the United States? How do I even sometimes know if I'm going to go to Amazon Web Services and just buy cloud hosting services for them? How do I even know where the data resides? There's a lot of very interesting computer science issues having to do with privacy and the intersection between privacy and scale. Because you can solve certain kinds of privacy issues if you're only working with a small set of data through various kinds of procedures. The question is, how do you make procedures that work when you're doing 1 million data records a second from 10,000 sources? So very interesting thing. The public health modeling. So we're doing this thing with the Centers for Disease Control and the Bill and Melinda Gates Foundation and another company on malaria modeling. And I think we're doing most of our modeling, malaria modeling in Madagascar. And we're using that as a place to kind of test out some of our ideas. And what we're doing is we're taking about 100 different models from all kinds of different specialists, and we're building a model of models that links them all together in real time. But all these specialists have intellectual property ownership of their model. And somehow we have to link all these models together to create this wonderful answer that will help the World Health Organization, the Center for Disease Control, do all this great stuff. But we have to get everybody to be willing to let it, drug companies and university researchers and et cetera, et cetera, et cetera. So again, it's a very interesting computer security and anonymization issue that's different, but obviously intersects with the privacy issue, all made very hard by the scaling issue. And that's the kind of problem that we like to take on. Okay, so we've actually built this model for the Centers for Disease Control. The Bill and Melinda Gates Foundation, they're funding vaccine development, so they've got all these models of how their, the molecular structure of their vaccine and models that predict how the malaria virus reacts to the drug and time phasing and all that stuff. And then so I have economic models coming from various places, and I have weather models and climate models and transportation models, and all these things come together in this big model, and we can make predictions about how various courses of action, when should I intervene on the third day? Should I intervene on the fifth day? People with what kinds of symptoms, when should I start treating them and stuff like that. So all these decisions. And so we can actually now pull all this data together and make projections of how to make this decision making. This is kind of our specialty, is things at these extreme scales. Million ingests per second, hundreds and thousands of petabytes of data, very high query rates simultaneous with the ingest, very complicated privacy and security structures, data that has to be partitioned, very complex anonymization. Those are the kinds of problems that we like to take on, whether it's for public health or whether it's for the government and so forth. We did something very interesting for New York. So after 9/11, one of the things that happened on September 11, 2001, is that all the emergency responders in the city of New York discovered that they really couldn't talk to each other. The police couldn't talk to the firemen. The police from Staten Island, who were coming over to help, couldn't talk to the police in Manhattan. All of the different frequencies and waveform modulations were complicated by the fact of all the buildings and the concrete canyons, and so multipath and loss of line of sight, and the fact that, of course, everybody in the eastern United States was trying to use their cell phone at the same time, and it was a real mess. And so the city of New York hired us to fix it. And one of the problems is, so we built this interesting system that uses a bit of spectrum that was allocated to New York by the federal government for this purposes, that we designed various mechanisms to deal with the multipath problems. So radio waves, they'll bounce around the concrete canyon, your receiver will get it 5 times at slightly different times, and how do you sort out which packet is the right packet, and how do you prevent the packet that arrives a little bit later after it's been reflected from jamming the signal for the packet that's supposed to be arriving at that time. That's called multipath. And lots of other things. But the main problem that had to be solved is that the total demand of all the people who wanted to do emergency and coordination services in a place as large as New York was too large for the spectrum that the Federal Communications Commission could allocate to them. So we had to invent whole new spectrum efficiency methods. Actually, there's a company that's down here in San Diego called Qualcomm that really kind of 20 years ago pioneered a lot of techniques for how to, as it were, they call it spread spectrum, but basically, hiding signals in noise and then extracting them. And we use derivatives of that technique to get, 10x kind of signal through the spectrum that the competitors were offering. And that made the New York system feasible. And so a year or so ago, you may have heard that there was a plane that took off from one of the airports in New York and crashed in the East River right after takeoff. And within about 2 minutes, there were boats, police boats and Coast Guard boats and private craft that had all been dispatched to go rescue all the people from the airplane. Nobody died. And nothing got overloaded. And despite thousands of people trying to use their cell phones at once, the cell towers didn't get blocked. And that was our comm system. So it actually kind of worked. So that's the sort of thing that we do. Next. So let me talk a little. I've said some of this. If you're going to work, if you're going to build, I mean, fundamentally, we are creators, right? Whether it's a little app for an iPhone or it's one of these big complicated systems that I like to work on, it's a creative process, and there's a whole series of things about being an effective creator that are kind of the artistic side, right? And I have found that the best computer scientists, the best system engineers, are those that acknowledge that and try to bring, kind of the holistic thinking that comes from the artistic side with the rigorous thinking that comes from the science and engineering side and bring that together. And by the way, it's a lot of fun, right? So I always tell people that, a system designer should be a scientist, engineer, but also an artist. And so, the hard science and the engineering drives the analysis, provides the rigor, prevents you from choosing solutions that are just ineffective or infeasible. But the art makes the system usable, makes the system attractive. Apple does this very well, right? There are 100 companies on the planet that make MP3 players, but Apple commands a huge price premium for theirs because they have thought about the user experience, right? And they have used what I would call art to make their MP3 players just more attractive, easier to use, more fun, however you want to describe it, right? And every product has a user, right? And that user is a person, and that person is concerned about all the same things that Apple's concerned about with their user. So, for example, with these military systems that I like to build, the users are under incredible stress, right? I've never been in the Army, but you can only imagine that, if you're in a helicopter or tank in combat, it's a very stressful situation. When people are under stress, they don't like complicated things, they make bad decisions, they don't like to have a lot of options, right? So you have to design the look and feel of your product with the user in mind, and that's the artistic side. So another thing that I like to talk about is, okay, you're going to come work for a company like us. How do you get ahead? People want to know, how do you have a successful career? How do you get advancement? How do you get promotion? It's not a mystery at all. So I've got this list of 4 things here. 5 things. You do those 5 things, you will be retained, you will be promoted, you'll be given responsibilities, you'll be given your choice of assignments, you'll be given your choice of where you want to work and live. You'll be the master of your situation. So there's no mystery here, and there's not a secret list, right? We like to tell people about this so that they can develop these characteristics, because that makes them more valuable employees to us, and then we will reward them and promote them. So obviously, you have to be technically excellent. You're here you wouldn't be here if you didn't have the capacity to do that. I already talked about that. We like people to take the time to get deep understanding of a customer domain, and not just one, right? Because it might be boring to spend your whole life working for one customer, right? So maybe you work for the Center for Disease Control for a few years, and then you go work for the City of New York, and then you go work for the Army, and then you go work for NASA, but in each phase, you take the time to learn something about the customer, so you have that domain knowledge and the engineering skills in one brain. Leadership is really important, and it doesn't mean that you have to take on being a manager of 1,000 people. Some people are excited by that and some people aren't. But that's not what we mean by leadership. I always like to say that the defining characteristic of a leader is that they can make people want to follow them. And you can do that whether you are the boss or not, right? It means being an opinion leader, being the person whose opinions people seek out, and you can help the team form consensus around the right kind of ideas. You do that whether you're the boss or not. In fact, I always remind our people that, we're not the military, and that people don't do what I say because I'm the boss. Most of the time they do what somebody says because they have been persuaded that it's the right thing. That you really lead by persuasion, and you don't have to be the boss to be persuasive. So all the characteristics I've talked about here, inspiring, motivating, forming consensus, challenging people to give their best, that's what I mean by a leader, accepting responsibilities, executing on those responsibilities, being reliable. Those are worth their weight in gold to an employer like us, to most employers, I'm sure. But that's kind of orthogonal to the question of whether you want to be the boss or whether we actually have what we call a dual career path. So, a whole series of formal steps and titles, being the boss of 3 people, being the boss of 10 people, being the boss of 30 people. I work for the sector president, and she has 25,000 people who work for her, right? So she is the boss. So you can think of it as the management career path. But we also have an individual performer career path. So I have somebody who works for me, who has never wanted to be the boss, has never wanted to actually have formal subordinates, sign time cards, things like that. He just wants to crack hard and interesting engineering problems. And we have a whole career path for people like that. And the best people are those who take the time to spend some of their career on one path and some of their career on the other. But, it's not a one-size-fits-all situation where the only way to get promotion and salaries and all that is to be the boss. It's not that way at all. At least not in our company. There's some other attributes that are good to demonstrate, right? But, you don't want to be, I don't want you to think that you stop learning the day you get your degree and you come to work for us. It's kind of the opposite. If anything, learning is likely to accelerate. It'll be different. It won't be about, fundamental things. But also, think of this. So I got my bachelor's degree in 1974. I was a mathematician in those days. I became a system engineer later on. Mathematics really, in some sense, hasn't changed that much. But I went to work for the company at first as a programmer. And programming has changed almost beyond description. Right? So there's a little bit of special circumstances, but the first computer I worked on, we had punch cards, it had discrete transistors, and it had honest-to-God core ferrite memories, 640,000 bits of core ferrite memory. It was the fastest computer in the world, control data 7600. They only built 2 of them. And it had discrete transistors. That was actually the way you got fast computers in those days. So it was a bit of an anomaly even then. But imagine how much, if I had stayed a programmer my whole career, how much I would have to learn. If I had stopped learning, I would be useless today, right? I wouldn't have a job, I wouldn't have a career. So you're going to continue learning even after you leave school and you go to work for us or somebody like us. And that, to me, that's great, right? It would be boring otherwise. This seems a little countercultural to some people. We love people who will seek out hard assignments because most people will run away from hard assignments. But the hard assignments are the ones that actually make the magic happen for the customers, right? And therefore for us. So we reward people that seek out hard assignments. I think I can point to 2 very specific things earlier in my career where I sought out hard, risky assignments and happened to succeed to some measure as the things that kind of set fire to my career. And people ask me, how did you get to be, the vice president and chief engineer of a large organization? It was more than anything else, it was that. And become an effective communicator. And when we talk about communications, people always talk about talking. Okay, I always like to talk about listening. The world needs good listeners. Right? Everybody likes to talk, but not everybody likes to listen. And writing is really important because when you operate on a large team, you don't have time to go around and talk to everybody. And written artifacts, whether they're text or whether they're engineering representations of data flow diagrams or whatever, are terribly important because that's how you operate at scale. That's how you codify decisions. That's how you rack up alternatives to assess. So writing is terribly important. And sometimes those of us who've chosen the science and engineering career are not all that interested in learning to write. Actually, writing is a very exciting and wonderful thing. Because it's how you can tell your story, and it's how you can be persuasive. And being persuasive is wonderful because it means you get your way, right? If you have a vision, the professor asked the question about, do you wait for customers to tell you that they need something, or do you invent something that they haven't thought of yet? Well, if you want to invent something that they haven't thought of yet, which, by the way, in my view, is the best and most rewarding thing in the whole planet, right, is to invent something that a customer hasn't thought of yet, and then you have to go to them and persuade them that this is a good idea. The way I like this, you have to transfer ownership of the idea from you to them. It has to become their idea. Then, of course, they'll hire you to build it because they actually know it was your idea. You do that by being persuasive, right? And so that will involve talking, but it will involve a lot of writing. Okay? But it is the enabler to the most exciting things in our field. That is the ability to make your mark, have an idea, have it realized, and see the benefit to society and the financial benefit to you and the company that comes from having that happen. Right? Next time. So I promised a quick chart about my career path. So over here is the individual technical performer part of my career, and over here is the management part of my career. Right? So I started at the bottom. Literally, I worked on a 400-person project, and in those days they would make a big organization chart of the project on a big piece of paper, and everybody's name would be, and I can remember the first org chart, I was the last name in the lower right-hand corner of the chart. Once a year they updated it, and it happened to be that they did it about 4 weeks after I got there. There I was, the last name in the lower right-hand corner of the chart, right? Being a programmer. A year later, I had 2 employees working under me, and they called that a work package manager. So I had to actually hire somebody, and then I had to fill another position from an existing employee, which means I had to persuade somebody to come to work for me. So I got a little bit of flavor of that. Then I did other things, like working on proposals. This is a great opportunity. It's very creative. There's no baseline. You can invent it all. It's very stressful. It's hard work, short schedules, long hours, but it's intensely creative. And then they stuck me over here again, and I was managing, a group of 10 people, a group of 30 people. This was, at one point in my career, my only career aspiration. I wanted to be the chief engineer on a really big program. I thought that was nirvana. Woke up one day, I was 34 years old, and I was the chief engineer on a $1 billion program. And it was great. I had a wonderful team and a wonderful program manager who taught me a lot. And by the way, it was a program that was completely screwed up. It was in a lot of trouble, so it could only go up, right? So that's taking on the hard assignments, right? I spent 3.5 years on that program, turned it around, not just me, there were 500 people on the program, but I was the chief engineer, so I got some of the credit. Created a really wonderful product that 20-something years later is still in use, still very successful. The interesting thing is that I had completely ran out of ideas about what I wanted to do with the rest of my career. Maybe I'll just keep doing that. I had a mentor, I had a boss who said, let me take charge of your career for a few years. So he sent me off to do other things, to run proposals, to be a program manager, and eventually, when he retired, I became his replacement as what we call a division general manager, which is running a 2,000-person business with profit and loss responsibilities, basically running my own company. All of those jobs were wonderful jobs, great life experiences, and I never would have asked to do them. I never would have thought of myself as being the right kind of person to do those jobs. And it turned out that I had a mentor who knew better than I did what I could do. And he kind of, no, let me take charge of your career for a few years. Let me go do this. And then I did that for a few years, and then I came over to do the job I'm doing now as the CTO and chief engineer for the sector, and I've been doing that job for the last 10 years. Let me tell you, I am much more effective in that job as I did these jobs. It's because, right, our business consists of 5 divisions, each of them headed by a division general manager, all of whom know that I used to be a division general manager. I sat in their shoes. I did their job. So they look at me differently than if I had just been some scientist who had come up this path and had never sat in any of their jobs. Right? So this is not something that a lot of companies talk about, this kind of participating on both sides of the dual career path. But first of all, it's a lot of fun. And secondly, even if you want to end up over here, it increases your value. And if you want to end up over here, it increases your value, increases your perspective. And maybe the most important thing is, at least for me, when I was in my 20s, I didn't know. I didn't know what I wanted to do. And I thought the idea of me choosing at age 22 when I finished graduate school, what I wanted to do for the rest of my life was the silliest idea imaginable, right? I wanted to have the ability to be flexible and to learn and adjust and maybe change my career goals over time as I learned new things and as the world changed. And you can do that. You do not have to get yourself pigeonholed into, one perspective. So I started as a programmer. I became a system engineer. I became a manager. I've been a business development, a marketeer sort of person. You can do all those things. You can have that kind of flexibility, and you don't have to paste one label on you when you leave graduate school and stick with that forever. Next one. Now, kind of a little bit of advertising. So I've spent my career building these big, complex systems. I think it is gangbusters. I think it's a great way to spend, for me, it's been a great way to spend my life. You get to meet lots of people with lots of other skills, but you can't do a job like that. I mean, some of these jobs I've worked on have been 1,000 people. Okay, so people with all kinds of skills and perspectives. Yeah, it's kind of hard getting everybody to march in the same direction, but that's fun too, right? And you can take your ideas and get them realized into things that you can never do by yourself, right? You can build things that you can never do. And now, for a company like Northrop, this is our core business, is building these big complicated systems, whether it's an airplane, an unmanned airplane, or something else. It is, however, a team activity, right? So we talked about that before. To me, it's the best and most satisfying of all possible jobs. And it involves technology. It involves engineering processes. It involves that creative and artistic aspect we talked about. And it lives and dies on whether you can create competitive differentiation in the marketplace. So I think that's my last chart.
Okay, great.
Yeah. So
Question.
Sir.
then how would you contrast, say, Northrop Grumman with other defense contractors like Star or Lockheed Martin?
Okay, so great question. Let me caveat that this is just my opinion, right? So and that it's not an unbiased opinion. So I'll warn you of that. So companies have character, right? And whether it's the founder's character or the current leader's character, but I'll tell you something that really matters to me that I found. So our company was founded by two engineers named Ramo and Woolridge. So TRW stands for Thompson, Ramo, Woolridge. Thompson died 100 years ago, was in the auto parts business. But Simon Ramo is still alive. He's 98 years old, but usually credited as the inventor of the formal discipline of system engineering. And ever since then, our company has been ran by engineers. And if you go onto the web and look at some of the other big engineering companies, Boeing, Lockheed Martin, they are ran by either attorneys or MBAs. And to me, that is reflected in the culture of the company. Boeing, I caveat that this is just my opinion, right? In my view, Boeing is like the military. You do what you're told. Rank matters a lot. Other companies in the engineering business are not like that. They're more like us. But companies really do have culture and character. And to me, the first order indication is who's the person who runs the company, right? So our chairman, his name is Wes Bush, is an engineer. Got a master's degree in engineering from MIT. Spent actually most of his whole career at our company building spacecraft. That's the part of the company he grew up in. There are other companies in the business, in the defense business or in the general engineering business that are ran by engineers, ran by scientists. There are a different set of companies that are ran by MBAs and attorneys. And I submit that those companies have really different cultures. And for me, I prefer the culture of the companies that seem to be the ones ran by engineers. You mentioned SPAWAR. I don't know if you all know what SPAWAR is. It's the Navy Engineering Center, so it's actually the civilian employees, but they work for the United States Navy. And it is actually kind of a competitor of ours because they build stuff for the Navy. So sometimes the Navy builds things with their own engineers rather than competing them out to private industry. I find that SPAWAR's culture is more like an organization that's ran by lawyers and business people because it's ran by all the rules of the United States government rather than a private company. That's just, you asked, and I caveated that this is my personal opinion. So, that doesn't mean that a company like Boeing can't create some wonderful products, right? It just means that the experience from the point of view of an individual employee will be different. Right? The 787 appears to be a pretty interesting product, right? And for example, a very good friend of mine is my counterpart at Boeing, and we collaborate on a lot of research. I don't mean to demean them. It's a different culture. Any more questions? Were you out? Well, thanks so much for being so attentive for an hour and a half, and glad to have met you all.